settle into the sleepy mind channel. Tonight, we will follow the journey of honey from hidden nectar to the quiet darkness of the hive, where thousands of bees work together in one of nature's most remarkable systems. By the end of this exploration, a simple spoonful of honey may never seem ordinary again. And if you enjoy calm educational sleep stories like these, feel free to like and subscribe, and explore the playlist filled with relaxing topics designed for long nights of listening. Honey has existed on Earth for longer than human civilization itself. Bees were already producing honey millions of years before the first cities appeared beside rivers or the first farms spread across ancient landscapes. Long before roads, electricity, books, clocks, or modern machines existed, bees were already traveling between flowers and storing honey inside hidden nests sheltered within hollow trees, cliffsides, forests, and grasslands. Human beings discovered honey thousands of years ago and quickly understood that it was something rare. In the ancient world, concentrated sweetness was difficult to find in nature. Honey became valuable across many early cultures because it provided energy, flavor, preservation, and lasting storage in a way few natural foods could match. Ancient cave paintings discovered in Spain appear to show people gathering honey from wild bee colonies more than 8,000 years ago, while sealed jars of honey were later placed inside Egyptian tombs, where some remained preserved for astonishing lengths of time. Even now, honey still feels slightly mysterious compared to many ordinary foods. A spoonful resting inside a jar appears calm and simple, yet its creation depends upon thousands of living insects performing many small actions over time. Honey does not appear suddenly. It begins as thin, watery nectar, hidden deep inside flowers growing across fields, orchards, forests, gardens, mountains, and meadows throughout the world. Bees gather tiny amounts of this nectar flower by flower and transform it into a concentrated substance that can last for years when properly stored. The process involves chemistry, airflow, evaporation, instinct, geometry, and cooperation between thousands of bees living together inside the hive. The amount of labor required to create honey is difficult to imagine at first. A single bee may visit hundreds of flowers during one journey away from the hive, collecting only tiny droplets of nectar from each blossom before moving on to the next. To humans, a spoonful of honey may seem insignificant because it disappears in seconds, yet for bees that same amount represents a large collection effort repeated across many flights. Entire colonies work together for weeks and months to build enough honey reserves to survive periods when flowers disappear from the landscape. Some estimates suggest bees may collectively travel distances equal to circling the Earth several times over, simply to produce a single pound of honey. No individual bee creates honey alone, because the hive depends upon cooperation at every stage of the process. Flowers themselves stand at the beginning of the system. Flowering plants produce nectar as part of a relationship that developed slowly over immense time. Nectar is a sweet liquid formed inside flowers to attract pollinators, including bees. The liquid contains sugars dissolved in water, along with tiny amounts of additional compounds that may influence scent and flavor. Flowers benefit when bees arrive because pollen can spread between blossoms during each visit, supporting reproduction across plants. Bees benefit because nectar provides an energy-rich food source that supports the intense activity required inside the colony. Entire ecosystems depend upon these exchanges taking place daily across forests, farms, orchards, wildflower fields, and gardens. Different flowers produce different nectar, which is why honey can vary greatly depending on where it originates. Honey produced near orange blossoms may carry a light citrus aroma, while honey gathered from clover fields, mountain wildflowers, eucalyptus groves, or lavender plants may develop entirely different flavors and colors. Some honey appears pale gold beneath sunlight, while other varieties become dark amber or brown. Soil conditions, rainfall, temperature, season, local vegetation, and climate all influence the nectar available to bees. Every jar of honey reflects a particular environment shaped by weather, geography, flowers, and the movement of bees across the landscape. Inside the hive, the atmosphere during honey season remains filled with steady, purposeful movement from morning until evening. Bees leave the hive repeatedly searching for flowers that are actively producing nectar. Some flowers release nectar more heavily during certain hours, depending on temperature and sunlight. Bees gradually learn these patterns and return to productive locations again and again while conditions remain favorable. Foraging routes may stretch across fields, orchards, and gardens as bees travel outward from the hive, searching for reliable nectar sources. Returning bees bring back tiny portions collected from hundreds of separate blossoms, and over time these repeated journeys build the colony's reserves. One of the most fascinating aspects of honey production is that bees are not gathering nectar simply to create sweetness. Honey functions as stored energy for the survival of the colony. During warmer seasons, when flowers are abundant, bees gather and store more food than they immediately require. Those reserves become essential later when colder weather arrives or flowers temporarily disappear from the landscape. Honey allows the colony to survive periods of scarcity because it provides concentrated nourishment stored safely inside the hive. Every drop represents survival, preserved through careful preparation during times of abundance. The hive itself operates like a living organism made from thousands of smaller individuals performing specialized tasks. Some bees focus on cleaning and maintaining the interior spaces of the hive, while others care for developing young. Some produce wax used to construct honeycomb, while others regulate airflow by moving their wings rapidly near hive entrances. Bees gather nectar and pollen outside before returning to transfer their collected resources deeper into the colony. No central leader directs these activities as humans might expect. Instead, the hive functions through instinct, scent, signals, and repeated behavior refined for millions of years. The honeycomb hidden inside the hive is equally remarkable. Bees construct repeating wax cells arranged in geometric patterns that maximize storage while using minimal material. The structure provides strength, efficiency, and organization together. Honey eventually fills these cells after nectar has been transformed and concentrated through processes unfolding inside the colony. Fresh nectar arriving from flowers contains far too much water to remain stable for long, so bees must change it through evaporation and chemical processing before honey finally forms. Air circulates through the hive, while moisture slowly decreases and the liquid thickens over time. Perhaps the most remarkable part of honey production is how ancient the process truly is. Long before human civilization emerged, bees were already gathering nectar beneath flowers and storing honey inside hidden colonies. Entire ecosystems evolved alongside these interactions between insects and flowers. Forests, orchards, gardens, farms, and wild landscapes still depend heavily upon pollination, taking place through the movement of bees between blossoms. Hidden behind the quiet simplicity of honey rests an enormous natural system connecting plants, insects, climate, chemistry, survival, and cooperation together across nature. Tonight, we will explore every stage of this remarkable process in calm, careful detail. From flowers producing nectar beneath sunlight, to bees traveling out across the landscape, to the hidden activity unfolding deep inside the hive, where thin, watery nectar transforms into concentrated honey, stored inside wax comb, through patience, airflow, chemistry, and the work of thousands of bees moving together as one connected colony. When a bee leaves the hive searching for nectar, the journey begins with movement across a large and continually changing landscape, filled with flowers competing for attention. To human eyes, a field of flowers may appear peaceful and still, yet to a foraging bee, it functions more like a vast network of signals, scents, colors, and food sources spread across the environment. Bees travel from flower to flower, collecting nectar in tiny amounts, often visiting hundreds of blossoms during a single trip away from the hive. These journeys may stretch across gardens, orchards, meadows, forests, farmland, and roadside plants depending on the season and the availability of blooming flowers. Each successful return flight adds only a small amount of nectar to the colony, yet thousands of repeated journeys support the production of honey inside the hive. Bees do not move randomly through the landscape. They gradually learn where productive flowers are located and often return repeatedly to the same areas while nectar remains available. Certain flowers produce nectar more heavily during certain times of day, depending on sunlight, temperature, and moisture conditions. Bees adapt to these changing patterns with remarkable efficiency. A patch of flowers producing rich nectar in the morning may become less productive later in the afternoon, while another area begins releasing more nectar as temperatures rise. The hive depends upon many bees exploring and responding to environmental changes unfolding across the landscape. One of the most fascinating aspects of bee foraging is the precision with which bees gather nectar from flowers. Bees possess specialized mouthparts designed specifically for collecting liquid food. Near the flower, the bee extends a long, flexible tongue-like structure that can reach deep into blossoms where nectar is stored. Different flowers vary in shape and depth, and some blossoms hide nectar far below the petals, where only certain pollinators can reach it. The bee draws nectar upward through these mouthparts before storing the liquid internally for transport back to the hive. Many flowers evolve specifically to attract pollinators, including bees. Bright colors, ultraviolet patterns invisible to humans, scent compounds drifting through the air, and shaped petals all help guide bees toward nectar sources. Some flowers even contain markings that function like landing guides, directing insects toward the nectar hidden inside. As bees move between blossoms gathering food, pollen grains attach to the tiny hairs covering their bodies and later spread to other flowers during future visits. This pollination process supports plant reproduction across entire ecosystems, while simultaneously providing food for the hive. Once nectar enters the bee's body, something interesting occurs. The nectar is not stored inside the same area used for digestion. Instead, bees possess a separate storage chamber, often called a honey stomach or crop, that temporarily holds the collected nectar during transport. This specialized storage system allows the bee to carry liquid food back to the hive without immediately digesting it for personal energy use. In some ways, the bee functions like a tiny flying transport vessel, carrying raw material from flowers back to the colony, where the larger transformation process will continue. The distinction between digestion and storage is important for honey production. If the nectar were digested immediately, it could not later be processed into stored honey for the colony. The honey stomach allows bees to gather and transport nectar while preserving it for transfer inside the hive. During productive foraging trips, bees may fill this storage chamber before returning home. Even so, the actual amount carried by a single bee remains very small from a human perspective. Flight itself requires a large amount of energy for such a small insect. A bee beats its wings incredibly rapidly while traveling between flowers and the hive, maintaining precise control even in changing wind conditions. During warmer months, the landscape surrounding an active hive may contain constant invisible movement as thousands of bees travel outward and return carrying nectar and pollen gathered from many plants. The air around flowering fields fills with these repeated journeys, happening hour after hour all day. Bees also possess impressive navigational abilities, allowing them to relocate productive flower patches across large areas. They use a combination of sunlight, visual memory, scent recognition, and sensitivity to polarized light patterns in the sky to navigate successfully. Even when clouds partially cover the sun, bees can often still orient themselves accurately enough to travel between flowers and the hive. Returning bees later communicate information about productive nectar sources to other bees inside the colony through movement patterns and physical interaction, allowing the hive to concentrate activity around rich food sources while flowers remain in bloom. The collection of nectar represents more than simple feeding behavior. Every foraging flight connects the hive to the environment. Weather conditions influence flower growth. Flower growth influences nectar production. Nectar availability influences bee movement and colony activity. The landscape itself shapes the flavor, aroma, and composition of the honey stored inside the hive. Fields of clover, orchards of citrus trees, mountain wildflowers, eucalyptus groves, and forest blossoms all contribute different nectar sources that later influence the honey produced by the colony. From a distance, a bee moving between flowers may seem insignificant against the scale of nature. Yet each tiny droplet of nectar collected during those flights becomes part of a much larger system unfolding inside the hive. Thousands of bees leave and return carrying nectar gathered from the landscape, flower by flower. Collection begins the transformation process before honey exists, because every drop arriving at the hive represents the beginning of a remarkable chain of biological and chemical changes that will continue inside the colony. As bees return to the hive, carrying nectar gathered from flowers across the landscape, another important stage of honey production begins inside the colony. The nectar arriving from outside is still thin, watery, and far from becoming honey. At this point, it more closely resembles sweet plant liquid than the thick golden substance stored inside honeycomb cells. The hive must now continue the transformation through a series of biological and chemical processes carried out by thousands of bees working together within the darkness of the colony. The entrance to an active hive during warmer seasons is filled with near-constant movement. Returning foragers arrive carrying nectar collected during flights that may have stretched across fields, gardens, orchards, forests, or wildflower meadows. Some bees return heavily loaded after discovering rich nectar sources, while others arrive carrying smaller amounts gathered from many separate flowers. The colony functions like a living network, where resources gathered outside are transferred inward to support the system operating inside the hive. Once a foraging bee enters the hive, the nectar stored inside the honey stomach is passed to another bee waiting inside the colony. This transfer occurs mouth to mouth through a process called trophallaxis. To human observers, the action may appear unusual at first, yet it is a major part of honey production because it allows nectar to move slowly through different stages of processing inside the hive. The returning bee regurgitates a small droplet of nectar, which is then received by another bee deeper inside the colony. This may repeat multiple times between different bees before the nectar is placed into the honeycomb. The transfer process serves several purposes at once. First, it allows nectar gathered by foragers to spread inside the hive where processing work continues. The nectar arriving from flowers contains complex sugars mixed with a high water content, and these sugars must slowly change before stable honey can form. Bees accomplish this transformation not through machines or external tools, but through biological compounds produced naturally inside their own bodies. Enzymes introduced during nectar transfer begin breaking down some of the more complex sugars into simpler forms. One important enzyme called invertase helps separate sucrose into glucose and fructose, which later become major components of honey itself. Other enzymes contribute additional chemical changes that support preservation and stability as the process continues. Although these reactions occur invisibly on a microscopic scale, they are essential to transforming nectar into lasting honey that resists spoilage over time. Nectar does not suddenly become honey in a single moment after entering the hive. Instead, the transformation unfolds as enzymes continue interacting with the liquid during repeated transfers and later stages of storage. The colony operates through patience and repetition, with thousands of tiny actions combining into a much larger process unfolding hour after hour inside the hive. Inside an active colony, bees continually move throughout the honeycomb, carrying nectar between cells and neighboring bees. The hive may contain tens of thousands of individuals during peak seasons, yet despite the crowded conditions, the colony remains organized. Returning foragers often interact quickly with interior bees before departing again in search of additional flowers. This steady circulation of bees and nectar allows honey production to continue while flowers remain available. Temperature inside the hive also plays an important role during this stage of processing. Honeybee colonies regulate internal conditions, maintaining warmth suitable for both developing young and food processing activities. The crowded movement of bees generates heat naturally, while bees also respond actively to temperature changes inside the hive. Stable warmth supports the ongoing chemical reactions and evaporation processes that will later reduce moisture levels within the nectar. As nectar moves from bee to bee, the liquid gradually changes in subtle ways. Moisture content remains high at first, yet enzymes continue altering the sugars, while repeated handling exposes the nectar to air inside the hive. The texture begins shifting from thin nectar towards something denser and more stable. Now the process still remains incomplete, but the transformation has begun inside the colony. The relationship between foraging and processing also reveals how specialized the roles inside the hive truly are. Some bees focus on gathering nectar outside. Others remain inside the hive receiving, transferring, and processing incoming food. Younger bees often handle more interior tasks, while older bees take on the risks of outside foraging flights. This division of labor allows the colony to operate while maintaining continuous food production during productive seasons. One of the remarkable things about this entire system is that no bee understands the larger process in the way humans might imagine understanding a plan. Individual bees respond to instinct, scent, physical interaction, temperature, and conditions rather than conscious, lasting planning. Yet together, the colony achieves something organized and effective through many repeated behaviors refined for millions of years of evolution. Deep inside the hive, the nectar gathered from flowers across the landscape continues moving through the colony from bee to bee. Enzymes begin reshaping the sugars hidden within the liquid, while thousands of bees support the larger process through cooperation and constant activity. What began as thin, watery nectar inside blossoms has now entered the hidden interior world of the hive, where chemistry, biology, and collective behavior guide the transformation toward honey. Inside the hive, the transformation of nectar into honey continues through a series of chemical changes unfolding within the liquid. The nectar gathered from flowers still contains a high water content levels and complex sugars that would spoil easily if left unchanged. At this stage, the colony has only begun the long process of turning raw plant nectar into stable honey. The work now depends upon time, repeated handling by bees, controlled conditions inside the hive, and ongoing chemical reactions taking place within the nectar as it moves through the colony. One of the most important parts of this transformation involves the gradual breakdown of sugars contained inside the nectar. Fresh nectar often contains a high amount of sucrose, a more complex sugar that bees begin changing through the addition of enzymes during repeated nectar transfers. These enzymes continue working after the nectar enters the hive, separating complex sugars into simpler forms, including glucose and fructose. The process unfolds gradually, with reactions progressing in the liquid over time. The chemistry involved may sound complicated at first, yet often the process resembles other familiar transformations found throughout food preparation and nature. Bread dough changes slowly while rising. Fruit ripens as chemical compounds shift within the flesh. Leaves change color during autumn as pigments break down and new colors emerge beneath the surface. Inside the hive, nectar also changes step by step through invisible reactions that slowly alter its composition and prepare it for lasting storage. Bees continue handling the nectar repeatedly as these reactions unfold. Some bees receive nectar from returning foragers, while others transfer and process the liquid deeper inside the hive. The repeated movement between bees exposes the nectar to additional enzymes and air, while also spreading the work across thousands of individuals inside the colony. The hive functions like a coordinated processing system where many small interactions contribute to the gradual transformation taking place inside the nectar. At first, the liquid remains very thin because nectar contains such a high water content. If humans were to taste nectar from many flowers, it would often seem mild and watery compared to honey. The sweetness exists, but the liquid lacks the concentrated texture people associate with honey resting inside jars or honeycomb cells. The colony must continue changing both the chemical composition and the moisture level before honey becomes stable. As processing continues, the nectar begins thickening. The change may seem subtle from moment to moment, yet over time, the difference becomes significant. Water content slowly decreases while sugars become more concentrated within the mixture. The texture shifts little by little away from thin nectar toward the denser consistency associated with honey. This thickening process depends upon both chemistry and evaporation working together inside the hive. The interior environment of the hive supports these changes in remarkable ways. Thousands of bees moving continually through the colony help maintain stable warmth and airflow, while wax comb provides organized storage areas for partially processed nectar. Conditions inside the hive remain active and controlled despite the crowded population. The colony responds to temperature, moisture, airflow, and food availability, while the transformation process moves forward. The repeated breakdown of complex sugars serves important purposes beyond sweetness alone. Simpler sugars become easier for bees to use as energy during colder seasons when stored honey supports survival inside the hive. The changing sugar composition also contributes to the lasting stability of honey itself. Over time, the mixture slowly becomes less suitable for microbial growth and spoilage as both chemistry and moisture levels continue shifting within the liquid. A useful detail in honey production is how the process unfolds compared to many modern human expectations. In human industry, machines often produce finished products rapidly through intense mechanical activity. Honey production depends instead upon many repeated actions carried out patiently over time. A returning bee transfers nectar, another bee receives it. Enzymes continue working inside the liquid. Moisture decreases. Air circulates through the hive. Thousands of bees repeat these activities while the nectar slowly transforms. The hive operates through accumulation rather than sudden change. No dramatic moment announces the instant nectar becomes honey. Instead, the liquid moves slowly through stages of processing, while the colony supports every part of the transformation. Even the thickening of the mixture happens slowly enough that it would be difficult to notice moment by moment inside the hive. Yet hour after hour, the chemistry continues progressing. The organization of the colony makes this possible on a large scale. Different bees contribute to different stages of the process, while the hive maintains stable conditions suitable for continued transformation. Wax comb expands as needed. Nectar arrives from outside flowers. Bees move through the hive, transferring, processing, and storing liquid across the comb. Every part of the colony supports the larger goal of building reliable reserves for survival. As the nectar thickens and chemical reactions continue unfolding, the liquid begins moving closer to honey, though important stages still remain ahead. Water content must continue decreasing before the mixture becomes stable. Airflow inside the hive will soon become even more important as bees work to remove excess moisture from the nectar stored in the honeycomb cells. One of the greatest challenges bees face during honey production is the very high water content found inside fresh nectar. Nectar gathered from blossoms is far thinner and more watery than the honey people recognize inside jars or honeycomb. In many flowers, nectar may contain well over half water, which means the liquid would spoil, ferment, or support microbial growth if stored in that condition for long periods. Bees must remove much of this moisture before stable honey can finally exist inside the hive. The entire colony works together to accomplish this transformation through careful storage, airflow, evaporation, and repeated handling of the nectar over time. At first glance, reducing water content may not sound difficult, yet inside the hive, it becomes a major part of the entire honey-making process. The difference between watery nectar and preserved honey depends heavily upon moisture levels. Too much of water allows microorganisms, including yeast, to grow more easily within the liquid. Lower moisture creates a more stable environment where spoilage becomes much less likely. Bees spend large amounts of energy slowly concentrating the nectar until honey becomes dense enough for lasting storage. After nectar has passed through several bees inside the hive, portions of the liquid are placed into the honeycomb itself. The honeycomb acts as both storage system and processing surface during this stage. Bees spread thin layers of nectar across the interior walls of wax cells, so a larger amount of the liquid becomes exposed to air. This increased surface area allows moisture to evaporate more from the nectar, while chemical changes continue unfolding inside the hive. The honeycomb may appear simple from a distance, yet it represents one of nature's most efficient structures. Bees construct the comb entirely from wax produced by their own bodies. Bees possess special wax-producing glands located beneath sections of the abdomen. Under the right conditions, tiny scales of wax emerge from these glands and are collected by the bees using their legs and mouth parts. The wax appears pale and soft before being shaped into the repeating hexagonal cells that fill the hive interior. Producing wax requires considerable energy from the colony. Bees consume a large amount of honey to create relatively small quantities of wax, which is one reason the hive constructs combs so efficiently. The repeating hexagonal pattern allows the colony to maximize storage space while using minimal building material. Mathematicians and engineers have studied honeycomb geometry for generations because the structure balances strength, efficiency, and space conservation. Each wax cell supports neighboring cells, creating a lightweight yet durable framework that can hold large quantities of honey. Inside the hive, newly deposited nectar glistens along the walls of the comb, while bees continue moving through the colony, performing many small tasks. Some bees add nectar to partially filled cells, while others inspect, clean, or reshape sections of the comb. Thousands of bees navigate through darkness using touch, scent, vibration, and memory, while the colony supports the gradual concentration of nectar unfolding across the honeycomb. The spreading of nectar into comb cells serves another important purpose beyond storage alone. Thin layers of liquid lose moisture more than deep pools because more surface area becomes exposed to air. Wet clothing dries faster when spread outward rather than left bundled together. Shallow puddles disappear more quickly than deep containers of water. Soup thickens more when simmered across a wide surface rather than trapped inside a narrow vessel. Inside the hive, bees apply this same principle naturally by distributing nectar across wax cells where evaporation can occur faster. Temperature inside the hive also supports the reduction of moisture. The crowded movement of thousands of bees helps maintain stable warmth inside the colony, while the enclosed structure protects the comb from outside environmental extremes. Warm air passing across exposed nectar surfaces slowly carries moisture away from the liquid. Although the process happens slowly, constant activity inside the hive allows evaporation to continue hour after hour. The relationship between nectar and wax comb reveals how deeply interconnected every part of the colony truly is. Flowers provide nectar outside the hive. Bees transport it inward. Bees process and transfer the liquid between one another. Wax-producing bees build and maintain inside the comb, where nectar spreads into thin layers. Air movement later increases evaporation, while chemical changes continue unfolding within the liquid. Every stage depends upon thousands of bees contributing specialized tasks that support the system operating inside the hive. At this stage of production, the nectar still remains far from becoming honey. Water content continues decreasing, while the liquid thickens little by little inside the comb. The scent of nectar, wax, warm air, and living bees fills the interior of the hive, while the colony continues working beneath the darkness of the comb. Outside, more bees still travel between flowers, gathering nectar from the landscape, bringing additional raw material back into the hive, where processing never stops during productive seasons. One of the most remarkable aspects of honey production is the patience built into the process itself. Bees do not rush the transformation because stability depends upon gradual concentration over time. Moisture leaves the nectar while enzymes continue changing the sugars within the liquid. Wax comb holds and organizes the material, while thousands of bees support the environment needed for evaporation and storage. The hive functions through repetition, consistency, and cooperation, carried out across many days and weeks. As nectar continues spreading across the wax cells of the honeycomb, the hive begins relying more heavily upon a major physical process involved in honey production: evaporation. Fresh nectar arriving from flowers still contains far too much water to remain stable for long periods, and although enzymes have already begun changing the sugars inside the liquid, moisture reduction now becomes essential. Without enough water leaving the mixture, the nectar could never transform into lasting honey. The colony must create conditions inside the hive that encourage evaporation while protecting the developing honey from contamination and environmental instability. The structure of the honeycomb plays a central role during this stage. Each wax cell acts not only as a storage chamber, but also as a designed processing surface where moisture can slowly escape from the nectar. Bees spread thin layers of liquid across the interior walls of these cells, rather than allowing the nectar to remain gathered in thick, deep pools. This arrangement dramatically increases the amount of exposed surface area available for evaporation. The greater the exposed surface, the more water molecules can leave the liquid and enter air inside the hive. Wet clothing dries faster when spread outward across a line rather than left folded in a pile. A shallow tray of water evaporates more quickly than a deep, narrow container holding the same amount of liquid. Sauces and soups become thicker while simmering because water slowly escapes upward into the air. Inside the hive, bees rely upon this same natural principle while processing nectar. By distributing the liquid across thousands of open wax cells, the colony creates ideal conditions for steady moisture reduction across the comb. The hexagonal cells provide large collective surface area while allowing bees to organize and store nectar within compact space. Every section of comb contributes to both storage and evaporation together. Some cells may contain freshly deposited watery nectar, while neighboring cells hold thicker, partially processed liquid closer to becoming honey. Throughout the hive, thousands of individual cells participate in different stages of transformation simultaneously. As moisture leaves the nectar, the mixture slowly becomes more concentrated. The sugars already altered through enzymatic activity now occupy a larger proportion of the remaining liquid. The texture thickens little by little, while the chemical environment becomes increasingly stable. At first, the changes remain subtle and difficult to notice from moment to moment. Yet over hours and days, the difference becomes significant as the watery nectar shifts toward the dense consistency associated with honey. Air movement inside the hive becomes important during this stage because evaporation depends heavily upon circulation. Without steady airflow, moisture would accumulate inside the hive environment and slow the concentration process considerably. Bees help regulate internal air conditions through coordinated movement and constant activity inside the colony. The hive itself behaves like a living climate-controlled system where thousands of insects respond to heat, humidity, and moisture. Bees move continually across the comb while evaporation continues from open nectar cells. Some bees inspect partially filled cells, while others transfer additional nectar into available spaces. Returning foragers continue arriving from outside, carrying fresh liquid gathered from flowers across the landscape. The hive contains nectar at many stages of concentration together, from freshly gathered watery liquid to thicker, nearly completed honey, approaching lasting stability. A useful detail in this process is how dependent honey production remains upon patience and repetition rather than speed. Humans often associate manufacturing with rapid machines and immediate results, yet bees achieve honey production through thousands of small coordinated actions unfolding slowly over time. Moisture leaves the nectar one tiny amount at a time. Air moves through the hive. Bees continue redistributing liquid across the comb. The transformation advances through consistency rather than urgency. Reduction of water content remains necessary because the survival of the colony depends upon stable reserves. During colder months or periods when flowers disappear from the environment, bees rely heavily upon stored honey for energy. If excess moisture remained trapped inside the honey, fermentation or spoilage could threaten the colony's food supply. The hive invests a great deal of effort into reducing water levels before sealing honey safely inside the comb. Inside the hive, evaporation cannot continue without one important element working continually in the background: airflow. As nectar spreads across the honeycomb and moisture begins leaving the liquid, air slowly fills with water vapor. If this humid air remained trapped inside the enclosed hive, evaporation would slow dramatically, and the nectar would struggle to thicken properly. The colony must maintain continuous circulation throughout the interior spaces of the hive. Bees accomplish this not through mechanical systems or external tools, but through the rapid, coordinated movement of their own wings. At the entrance of an active hive during warmer months, certain bees may often be seen standing motionless, while vibrating their wings at remarkable speed. To a casual observer, the behavior may appear simple or repetitive, yet these bees are performing a major environmental control task inside the colony. Their wing movements generate steady airflow that passes through the hive and across the exposed nectar resting in the honeycomb cells. The wings of a honeybee beat incredibly rapidly during flight, and bees use these same powerful movements while ventilating the hive interior. Even though a single bee is tiny, thousands of bees working together can produce effective air circulation inside the colony. The hive behaves like a naturally regulated ventilation system, where airflow patterns shift depending on temperature, humidity, and nectar processing inside the comb. The movement of air serves several purposes at once. First, it removes humid air from around the nectar surfaces, allowing additional moisture to continue evaporating from the liquid. Second, it helps maintain stable internal conditions suitable for developing bees, food, and ongoing colony activity. Third, circulation prevents sections of the hive from becoming excessively damp, while nectar continues concentrating inside the open comb cells. A notable part of this process is how responsive the hive remains to changing conditions. On warm or humid days, bees may increase ventilation activity considerably as the colony works harder to control moisture levels. During periods of heavy nectar collection, when large amounts of watery liquid enter the hive, airflow becomes even more important because evaporation demand rises. Thousands of bees respond together automatically through instinct and environmental feedback without needing centralized direction. The interior of a hive during peak honey production is filled with layered activity unfolding simultaneously in every direction. Returning foragers arrive, carrying nectar gathered from flowers across the landscape. Interior bees transfer and process incoming liquid between one another. Wax comb holds nectar at various stages of concentration. Young bees develop within protected brood areas deeper inside the colony. Ventilating bees fan their wings near entrances and passageways, while warm air moves through the comb carrying moisture outward. Air movement across exposed nectar surfaces increases the speed of evaporation. Wet skin cools faster when wind passes across it because moisture evaporates faster. Clothing dries more quickly outdoors on breezy days than inside still enclosed rooms. A fan placed near damp surfaces helps remove moisture by replacing humid air with drier air. Inside the hive, bees apply this same principle naturally through wing-generated airflow circulating around the comb. As evaporation progresses, moisture levels within the nectar continue decreasing. The liquid grows denser as water leaves the mixture and sugars become increasingly concentrated. Fresh nectar may contain a high water content, while honey contains less moisture and far greater stability. The colony must guide the nectar through this long reduction process before safe lasting storage becomes possible. Temperature and airflow work together inside the hive. Warm conditions support faster evaporation, while circulation removes accumulating moisture from air. Bees regulate these conditions through both their movement and their positioning inside the colony. Some bees focus heavily on ventilation, while others continue processing nectar, maintaining comb, or gathering additional food outside. The hive resembles a living environmental control system, powered entirely through the activity of insects cooperating together. The sound inside an active hive reflects this constant movement. Thousands of wings vibrating at different speeds create a steady, layered hum, filling the interior spaces of the colony. Some vibrations come from bees moving across the comb, while others originate from bees deliberately fanning air through the hive. To humans standing nearby, the sound may seem uniform at first, yet inside the colony, the vibrations and airflow patterns help maintain the stable environment needed for honey production and survival. The reduction of moisture during this stage remains essential because stable honey cannot exist without sufficiently low water content. If too much moisture remained trapped inside the liquid, fermentation and spoilage could threaten the colony's reserves later during colder seasons when flowers disappear. Every movement of air through the hive supports the lasting survival of thousands of bees, depending upon stored honey for future nourishment. As moisture continues leaving the nectar through evaporation, the liquid in the honeycomb begins changing in noticeable ways. The watery consistency of fresh nectar slowly disappears as sugars become more concentrated within the remaining mixture. At first, the transformation remains subtle. A newly filled comb cell may still contain thin liquid moving easily across the wax surface, yet over time, the nectar becomes denser, heavier, and more resistant to movement. The process unfolds inside thousands of cells inside the hive, while bees continue supporting the conditions needed for concentration to continue. The gradual thickening of nectar is one of the clearest signs that the transformation toward honey is advancing successfully. Fruit juice simmered on a stove becomes thicker as water escapes into the air. Syrups become denser while heating continues. Even mud left beneath sunlight hardens and contracts as moisture disappears. Inside the hive, bees rely upon this same physical principle while guiding nectar toward a more stable and concentrated state. Unlike sudden chemical reactions that produce immediate visible results, honey formation depends upon slow, steady change unfolding over time. Every hour, a little more moisture leaves the nectar. Every hour, the sugar concentration rises slightly higher. Thin nectar develops the thick, smooth consistency associated with honey resting inside sealed comb cells or glass jars. The colony itself plays a direct role in controlling the conditions that allow this concentration process to continue successfully. Bees regulate airflow, maintain warmth, organize nectar storage, and respond to changes occurring both inside and outside the hive. During productive seasons, thousands of bees move continually through the colony, carrying nectar, maintaining comb, ventilating the interior, cleaning cells, feeding young, and supporting the larger process unfolding inside the hive. The environment surrounding the hive also influences how these changes occur. Warm, dry weather often supports faster evaporation because moisture leaves exposed nectar more easily under such conditions. Cooler or more humid weather may slow the process considerably. Heavy rainfall can reduce nectar production outside while also increasing moisture in air. Honey production does not occur separately from nature around the hive. Temperature, rainfall, sunlight, season, flowers, and air conditions all influence the pace and success of the process. Inside the hive, bees respond to these changing conditions. On warm, productive days, the colony may process large amounts of incoming nectar, while ventilation activity increases to manage moisture levels. During cooler conditions, movement patterns and hive activity may shift slightly as the bees maintain stable warmth and continue protecting developing honey reserves. The hive behaves less like a fixed structure and more like a living adaptive system, continually adjusting itself to the environment. A useful detail in honey production is how thousands of bees cooperate without needing centralized leadership or detailed planning as humans might think. Individual bees respond instinctively to temperature, scent, vibration, airflow, crowding, and nectar availability. Together, these many individual responses create organized colony behavior that supports lasting food production on a remarkable scale. The concentration of nectar depends not upon isolated effort from single bees, but upon the coordinated activity of the entire hive functioning together. As nectar thickens, its physical properties slowly begin changing. The liquid becomes stickier and more viscous as water content decreases. Movement inside the comb cells slows. Sugars dominate a larger percentage of the mixture, while the environment inside the liquid becomes more resistant to microbial growth. At this stage, the developing honey still contains more moisture than finished honey, yet the colony continues guiding the transformation toward greater stability. The wax honeycomb surrounding the nectar also supports this gradual concentration process. Rows of hexagonal cells hold partially processed liquid at many stages simultaneously. Some cells contain fresh nectar gathered from flowers, while neighboring cells may hold much thicker liquid approaching honey. Bees move between these cells while processing, redistributing, and monitoring the colony's reserves. As the water content inside the nectar continues decreasing, the liquid begins entering a major stage of the entire transformation process: stability. Earlier inside the hive, the nectar remained thin and vulnerable because high moisture creates conditions where fermentation and microbial growth can occur more easily. After long periods of evaporation, airflow, chemical change, and repeated handling by bees, the liquid becomes increasingly resistant to spoilage. The gradual reduction of water changes not only the texture of the nectar, but also the biological environment inside the mixture itself. Most microorganisms require sufficient moisture to grow and reproduce. Bacteria, molds, and many forms of yeast depend upon available water to survive. Humans encounter this principle continually in everyday life, even without noticing it. Fresh fruit spoils quickly because it contains high moisture. Bread left exposed to damp conditions often develops mold. Wet environments support decay more easily than dry ones. Throughout human history, many food preservation methods relied heavily upon reducing water through drying, salting, smoking, or concentration. Inside the hive, bees accomplish something similar through evaporation and sugar concentration while transforming nectar into honey. As moisture levels decrease, the environment inside the liquid becomes increasingly hostile to microbial growth. Sugars now dominate a much larger proportion of the mixture, while available water continues shrinking. The thickening honey begins creating conditions where many microorganisms struggle to survive or reproduce. This shift toward low moisture stability is one of the main reasons honey can remain preserved for such long periods when properly stored. The change does not happen suddenly in a single moment. Honey production remains a gradual process unfolding across the comb. Some cells still contain relatively fresh, watery nectar, while others hold thicker liquid, much closer to maturity. Throughout the hive, bees continue redistributing nectar, maintaining airflow, and supporting evaporation as the colony guides the mixture toward lasting preservation. A notable part of honey is that preservation emerges naturally from the combined effects of several processes working together at once. Low water content becomes one major factor, yet enzymes added earlier during nectar transfer also contribute to the stability of honey. The concentration of sugars influences microbial survival. Even the slightly acidic conditions found in honey help create an environment less favorable for spoilage organisms. The hive produces preservation not through a single mechanism, but through multiple overlapping biological and chemical changes unfolding together. Ancient cultures stored honey in sealed containers because it remained usable longer than many other foods available at the time. Archaeologists examining ancient tombs and buried storage vessels have occasionally discovered honey preserved after astonishing lengths of time. Although crystallization and thickening may occur naturally with age, the honey often resists the kind of widespread decay commonly seen in other foods exposed to similar timescales. The colony depends upon these reserves for survival during difficult seasons when flowers disappear from the environment. During colder months or periods of scarcity, bees rely heavily upon stored honey to provide concentrated energy while remaining sheltered inside the hive. Stability becomes essential because spoiled or fermented reserves could threaten the survival of the colony. The thickening texture of the liquid now reflects these changes occurring deep within the mixture. Fresh nectar once moved easily like thin sweet water, yet the developing honey slowly becomes smoother, denser, and more viscous as moisture continues leaving the comb. Bees moving across partially filled cells encounter liquid increasingly closer to honey in both texture and composition. The hive itself continues supporting these changes through environmental control. Air circulates through the colony, while bees maintain temperature and moisture balance across the comb. Ventilation activity removes humid air, carrying evaporated water away from the honeycomb. Thousands of bees continue moving through the hive, performing specialized tasks that collectively support preservation. Every stage of activity inside the colony contributes to the formation of stable honey reserves. A useful detail in this transformation is how it depends upon collective behavior. No individual bee could produce large, stable honey reserves alone. The process requires thousands of repeated flights between flowers and the hive, repeated nectar transfers between bees, constant ventilation, wax construction, environmental regulation, and ongoing chemical change unfolding over time. The final honey stored inside the comb represents the combined effort of the colony operating together as one connected system. By the time the nectar approaches its final stages of transformation inside the hive, the liquid has changed profoundly from the substance originally gathered from flowers across the landscape. Earlier in the process, nectar contained a high water content mixed with plant sugars and trace compounds produced by blossoms. After extended evaporation, enzyme activity, airflow, and repeated processing by bees, the chemical composition of the mixture has shifted dramatically. Water content has fallen, while sugars dominate the liquid. The result is no longer fragile nectar, but a concentrated and increasingly stable substance that can last for long periods inside the hive. One of the most important changes involves the balance of sugars within the honey. Earlier stages of processing allowed enzymes to break apart more complex sugars into simpler forms, including glucose and fructose. These simpler sugars now make up the majority of the honey. As moisture levels continue decreasing, the sugars become increasingly concentrated within the remaining liquid, giving honey both its sweetness and its thick, smooth consistency. The transformation may seem gentle from the outside, yet chemically the liquid has undergone a remarkable reorganization while moving through the colony. Fruit juice becomes sweeter and thicker when water evaporates away. Syrups grow dense as moisture decreases during cooking. Even dried fruit preserves flavor because sugars and nutrients remain concentrated after water leaves the flesh. Honey represents one of nature's most refined examples of this principle. Bees slowly remove enough water from nectar that the remaining mixture becomes heavily dominated by sugars, while still retaining enough fluidity for storage and future use. As sugars come to dominate the mixture, the structure of the honey stabilizes further. The low moisture environment now strongly limits microbial growth, while the dense concentration of sugars creates additional preservation effects within the liquid. The colony has essentially transformed fragile nectar into a durable food reserve that supports survival during difficult seasons. Stability becomes one of the defining characteristics of honey because the hive depends upon these reserves, lasting through periods when nectar can no longer be gathered outside. The thick texture of honey reflects these structural changes taking place within the mixture. Earlier nectar flowed easily through the comb because water remained abundant. Now the liquid moves more slowly as sugars become densely concentrated throughout the honey. Bees encounter a substance increasingly similar to the honey sealed within storage cells. The gradual thickening also helps reduce moisture exchange with air, further supporting preservation inside the hive. A useful detail in honey is that its preservation emerges naturally from biological and physical processes working together. Bees do not manufacture artificial preservatives or external chemicals. Instead, the colony relies upon evaporation, sugar concentration, enzymes, controlled airflow, warmth, and careful storage to achieve remarkable stability. Through patience and repetition, the hive creates conditions where honey can resist spoilage more than the original nectar ever could. Bees continue moving across the comb, while some cells contain nearly finished honey, and others still hold partially concentrated nectar, undergoing further evaporation. Air circulates inside the hive, while the scent of warm wax, nectar, pollen, and honey fills the interior. The colony functions without pause because preservation depends upon maintaining stable conditions across the honeycomb. Outside the hive, conditions continue changing from day to day. Weather shifts, flowers bloom and fade, temperatures rise and fall with the passing season. Yet inside the colony, the bees work to preserve energy gathered from the landscape in concentrated form. Every drop of honey represents sunlight captured first by flowers and then transformed through the labor of thousands of bees into stored nourishment that can last far beyond the blooming season itself. The lasting nature of honey has fascinated humans for thousands of years because it behaves differently from many other natural foods. Most liquids spoil quickly when left exposed over time. Fruits rot, juices ferment. Moist foods support mold and bacterial growth. Honey, however, resists these processes well when properly stored because its structure and chemistry create an environment unfavorable for many forms of microbial activity. Ancient people may not have understood the chemistry involved, yet they recognized honey's unusual durability and valued it for that reason. Inside the hive, preservation is not simply convenient, it is essential for survival. During colder periods or times when flowers become scarce, bees depend heavily upon stored honey for energy while remaining sheltered inside the colony. The hive invests a great deal of effort into achieving stable, lasting storage before sealing honey safely inside the comb. Every stage of evaporation, concentration, airflow, and enzymes contributes toward this final preserved state. Some cells hold fresh incoming nectar recently gathered from flowers, while others contain thick honey approaching full storage readiness. Bees continue inspecting and managing these reserves, while conditions inside the hive remain regulated through collective activity. Thousands of individual insects contribute small specialized actions that together produce one of nature's most effective food preservation systems. Once the honey inside the hive has reached a sufficiently low moisture level and stable composition, the colony begins preparing it for lasting storage in the honeycomb itself. At this stage, the transformation from nectar into preserved honey is nearly complete. The thickened liquid now rests inside thousands of wax cells spread across the comb, each cell functioning as an organized storage chamber within the larger structure of the hive. Bees continue inspecting, redistributing, and managing these reserves while the colony gradually shifts from active processing toward protection and preservation. The honeycomb serves as more than a simple container. Every section of comb supports the organization and lasting survival of the colony by holding reserves safely inside the hive. Rows of repeating hexagonal cells extend across the wax structure like an enormous natural storage network built entirely by bees themselves. Some sections may contain developing young bees, while others hold pollen or partially processed nectar. Certain regions, however, become dedicated largely to honey storage, where the colony preserves concentrated food for later use. Each individual cell stores only a little honey, yet together the honeycomb can hold remarkable quantities inside the hive. Thousands upon thousands of cells work collectively to organize the colony's resources in an efficient and compact arrangement. The repeating geometry allows bees to maximize storage while using minimal wax, creating one of the most elegant natural structures found anywhere among insects. The honey resting inside these cells represents the combined labor of many flights between flowers and the hive carried out over many weeks. As bees monitor the honey, they continue assessing whether the moisture level has become low enough for safe, lasting preservation. If the liquid still contains too much of water, further evaporation and airflow remain necessary before storage can be finalized. Once conditions become stable enough, however, another important stage begins inside the colony. The cells are sealed. Bees create these seals using fresh wax, produced from specialized glands beneath their abdomens. Tiny scales of wax emerge slowly from the bee's body and are shaped using legs and mouth parts, before being applied across the open top of a filled honey cell. The wax covering forms a protective cap, sealing the honey safely inside the comb. Across large sections of the hive, thousands of capped cells may create broad, pale surfaces covering the reserves beneath. The sealing process is one of the clearest signs that the colony considers the honey ready for preservation. Earlier stages of processing required open cells exposed to airflow, so moisture could continue leaving the liquid. Now the environment inside the honey has stabilized enough that the colony can protect it from outside humidity and contamination through wax sealing. The hive essentially closes and safeguards the finished reserves for survival. The appearance of capped honeycomb differs noticeably from cells still containing nectar or partially processed liquid. Newly deposited nectar often glistens with visible moisture inside open cells, while mature capped honey appears more solid and enclosed beneath pale wax caps. Experienced beekeepers sometimes examine these capped sections to determine when honey has reached proper storage readiness, because the bees themselves perform the final assessment regarding moisture stability. A useful detail in this stage is how the colony balances processing with preservation. Bees do not seal honey prematurely because excessive moisture trapped inside the comb could still allow fermentation or spoilage over time. The colony relies upon gradual concentration, airflow, evaporation, and ongoing inspection before committing energy towards sealing the cells. Every stage reflects patience, environmental awareness, and refined instinctive behavior developed across millions of years. The wax caps themselves also contribute to preservation by limiting exposure between the stored honey and the surrounding hive atmosphere. Once sealed, the honey becomes better protected from changes in humidity or contamination from external conditions. Inside the capped cells, the concentrated low-moisture honey remains stable while waiting for later use during colder seasons or times of scarcity. The atmosphere inside the hive during this stage reflects a colony preparing for lasting survival. Bees continue traveling out, gathering nectar while flowers remain available, yet deep inside the comb large sections of honey may already rest safely under wax. Air still circulates through the hive, while bees maintain temperature, cleanliness, and organization across the colony. Humans have admired honeycomb for thousands of years, partly because it reveals this hidden organization. So, breaking open a section of comb exposes rows of neatly sealed cells filled with concentrated honey, created entirely through the labor of the colony. Each capped cell represents many flower visits, repeated nectar transfers, chemical transformations, evaporation, ventilation, and careful environmental regulation carried out over time by thousands of bees cooperating together. The hive itself now resembles a vast living storehouse filled with preserved energy. Honey gathered from flowers across forests, gardens, and fields rests inside wax chambers protected beneath constructed seals. Outside, weather and seasons continue changing across the landscape, yet inside the hive, the colony has succeeded in preserving nourishment that lasts after flowers disappear from the environment. Once the honeycomb cells have been sealed beneath thin wax caps, the colony enters a stage focused heavily on preservation and lasting stability. The honey resting inside these capped chambers has already undergone large transformation since its earliest beginnings as watery nectar. Moisture levels have been reduced through evaporation and airflow, while sugars became concentrated throughout the liquid. Now the wax seals help maintain those stable conditions by protecting the honey from excess humidity and outside contamination. The colony has essentially created thousands of tiny storage vaults distributed across the comb, where reserves can remain secure for later use. One of the most important benefits of sealing the honeycomb is moisture control. Even after honey reaches low water content, Exposure to humid air could still allow the liquid to absorb additional moisture over time, because honey naturally attracts water from the environment. Inside an open cell, changing humidity conditions inside the hive might slowly alter the stability of the stored honey. By covering mature cells with wax, bees reduce this exposure and help maintain the concentrated state achieved during earlier stages of processing. Dry foods last longer when protected from moisture in sealed containers. Grain stored in damp conditions may spoil or grow mold more quickly than grain kept dry and protected. Even modern kitchens depend heavily upon packaging and storage systems designed to limit exposure to air and humidity. Inside the hive, bees accomplish something sophisticated through natural materials alone. Thin wax caps preserve concentrated honey while maintaining stable conditions inside each storage cell. The honey sealed beneath the comb is not meant for immediate consumption alone. These reserves exist to support the colony across periods when flowers may become scarce or entirely absent from the environment. During colder seasons, droughts, storms, or times of limited bloom, bees rely heavily upon the energy stored inside the capped honeycomb. The hive gathers, processes, preserves, and protects reserves because survival depends upon maintaining reliable, lasting resources. The organization of the hive plays a major role in making this possible. Honey storage areas are arranged across the comb, so the colony can access reserves while still supporting brood development, ventilation, movement, and daily activity inside the hive. The honeycomb itself functions like a living architectural system where every section serves multiple connected purposes. Some regions hold developing larvae, while others store pollen or incoming nectar. Mature honey reserves often occupy upper areas of the comb, where the colony can maintain stable conditions around the food. Efficiency shapes nearly every aspect of this arrangement. The repeating hexagonal cells maximize storage while minimizing the amount of wax required for construction. Bees move easily across the comb while transporting nectar, inspecting cells, ventilating the hive, or feeding developing young. Airflow continues circulating through open spaces, while the colony maintains temperature and humidity balance across the interior. Every structure and behavior supports survival through organization, repetition, and careful use of energy. The preservation of honey also reveals how closely connected the colony remains to the changing environment outside the hive. During times of abundant flowering, bees gather more nectar than they immediately require. This surplus allows the colony to build reserves for periods of scarcity. In years with favorable weather and strong nectar flow, colonies may store impressive quantities of honey beneath broad sections of capped comb. Poor weather, drought, or reduced flowering conditions, however, can limit nectar collection and place greater pressure on reserves later in the season. Inside the hive, bees continue monitoring conditions even after cells have been sealed. The colony maintains ventilation, cleanliness, and structural stability across the comb, while protecting food from threats, including moisture buildup or unwanted intruders. Thousands of bees remain active across the hive at all times, responding instinctively to changing conditions while preserving the integrity of the colony's resources. The capped honeycomb itself becomes one of the most visually striking parts of the hive. Broad, pale surfaces of sealed wax may stretch across entire sections of comb, while hidden beneath them, rests concentrated honey gathered from many flowers across the landscape. To humans examining a hive frame, the capped cells appear calm and orderly, yet each section represents weeks of labor carried out by thousands of bees performing repeated flights, nectar transfers, evaporation control, wax production, and environmental regulation. A useful detail in honey preservation is how naturally the process unfolds without external instruction or mechanical technology. Bees do not study chemistry, engineering, or food science as humans might think, yet through instinct and evolutionary refinement, the colony achieves an effective preservation system. Warmth, airflow, evaporation, enzyme activity, wax construction, and moisture control all work together to produce stable reserves that support survival through difficult seasons. For the bees living inside the hive, honey is more than a sweet substance resting within wax cells. Honey functions as the colony's primary lasting food reserve and a major resource supporting survival year-round. Every stage of honey production ultimately serves this single purpose: the gathering of nectar, the transfer between bees, the evaporation of moisture, the circulation of air through the hive, and the sealing of honey under wax, all contribute toward creating concentrated stored energy that the colony can depend upon when fresh food becomes difficult or impossible to gather outside. During productive seasons filled with blooming flowers, bees may collect nectar in quantities far greater than the colony immediately requires. Warm temperatures and abundant blossoms allow bees to travel between flowers and the hive, building reserves across the honeycomb. Yet the colony does not treat these productive periods as permanent conditions. Seasonal change shapes nearly every aspect of life inside the hive, because flowers appear and disappear year-round, depending on weather, rainfall, and daylight. As summer gradually shifts toward colder seasons in many parts of the world, flowers begin producing less nectar or stop blooming entirely. Temperatures fall, daylight hours shorten, rain, wind, frost, or snow may cover the landscape depending on the region. During these times, bees cannot reliably gather enough nectar to support the colony daily. The hive must instead depend heavily upon the preserved honey reserves stored earlier during times of abundance. The relationship between seasons and food availability has shaped bee behavior over time. Long before humans built hives or studied insects scientifically, wild bee colonies survived by learning through evolution to gather and preserve enough food before difficult seasons arrived. Colonies that failed to build adequate reserves often struggled to survive periods when flowers disappeared from the environment. Over many generations, the instinct to collect, concentrate, preserve, and protect honey became deeply connected to the survival of the species itself. Inside the hive during colder periods, activity changes noticeably compared to the intense movement of peak nectar-gathering seasons. Fewer bees leave the colony because flowers may no longer be available. Instead, bees remain clustered together inside the hive while relying upon stored honey for nourishment and energy. The reserves built during warmer months now become essential for maintaining warmth and supporting life inside the colony. Honey provides bees with a concentrated energy source from its dense sugar composition. Glucose and fructose contained within the honey can be metabolized by the bees to support movement, warmth generation, and ongoing colony activity. During cold weather, bees may cluster tightly together, while consuming honey slowly to fuel the muscular activity needed for heat production inside the hive. The reserves support not only feeding, but also temperature regulation and survival during harsh conditions. A colony cannot simply travel long distances searching for food during freezing weather or periods without flowers. The hive must survive using the resources already stored inside the comb. Every sealed honey cell represents preparation carried out before scarcity arrives. The colony succeeds because it transforms temporary abundance into preserved, lasting nourishment. The amount of honey required for survival may vary depending on climate and conditions. Colonies living in regions with long, severe winters may need large reserves to survive many months without nectar sources. In warmer climates where flowers remain available more consistently, bees may continue gathering nectar across longer portions of the year. A useful detail inside the hive is how the colony balances present needs against future security. Bees consume some honey for immediate energy, yet the colony also protects large portions of reserves for later use. During productive periods, bees continue gathering and preserving nectar even when significant honey stores already exist because conditions can change unexpectedly. Drought, storms, cold temperatures, or poor flowering seasons may reduce food availability rapidly across the landscape. The honeycomb itself becomes a physical map of this preparation. Rows of sealed cells hold preserved energy gathered slowly from many flowers visited over weeks or months. Every section of capped honey represents repeated journeys across fields, forests, orchards, and gardens by thousands of bees collecting tiny amounts of nectar flower by flower. The reserves contain the concentrated results of large collective effort spread across the colony. Bees move across the comb, accessing stored honey while remaining sheltered inside the colony. The warmth generated by clustered bees combines with the energy provided through honey consumption to maintain survival until favorable conditions return outside. The hive endures difficult seasons, not because flowers remain available, but because the colony prepared in advance. Outside the hive, the landscape changes continually with the passing of the seasons. Blossoms appear and fade, temperatures rise and fall, rainfall patterns shift across forests, grasslands, orchards, and gardens. Yet in the honeycomb, reserves gathered during times of abundance remain protected under wax waiting for future need. The colony survives uncertainty through organization, cooperation, and the careful preservation of stored energy collected from nature. The survival of a honey colony depends heavily upon the reserves stored inside the hive, because nature surrounding the bees changes continually year-round. Flowers bloom only during certain seasons. Weather patterns shift unpredictably. Rainfall, drought, heat, wind, and temperature all influence how much nectar becomes available across the landscape. The colony cannot rely upon continuous abundance. Instead, bees survive by transforming temporary periods of rich flowering into lasting stored honey reserves that support the hive during future scarcity. In years when conditions remain favorable, nectar may become abundant across fields, orchards, forests, gardens, and meadows for extended periods of time. Warm sunlight, regular rainfall, healthy flowers, and stable temperatures can create ideal conditions for nectar production. During these productive stretches, bees may leave the hive in large numbers every day, gathering nectar while flowers remain rich with resources. Abundance changes the rhythm of activity inside the colony. Foraging routes become productive, while bees inside the hive process large amounts of incoming nectar hour after hour. Honeycomb cells fill rapidly during strong flowering periods, and sections of honey begin spreading inside the hive beneath pale wax caps. The colony takes advantage of these favorable conditions because no productive season lasts forever. Every warm day filled with flowers becomes an opportunity to strengthen survival through additional reserves. The connection between honey production and the environment becomes clear during years when conditions are less favorable. Drought may reduce flowering across large areas. Heavy rain can wash nectar away from blossoms or prevent bees from flying safely. Cold temperatures may delay blooming seasons, while extreme heat can shorten the lifespan of flowers themselves. Even strong winds may interfere with foraging activity by making flight more difficult for bees traveling between flowers and the hive. When nectar availability declines, the colony must rely increasingly upon previously stored honey reserves. Bees may travel farther, searching for productive flowers while collecting smaller amounts of nectar during each trip. Inside the hive, preserved honey becomes more important because incoming food from the environment no longer arrives in the same abundance as before. Scarcity increases the colony's dependence upon the careful preparation completed earlier during more productive seasons. This balance between abundance and scarcity shapes nearly every aspect of bee behavior. During times of plentiful bloom, the colony gathers and stores aggressively because future conditions remain uncertain. During difficult periods, the hive becomes more dependent upon the reserves already protected inside the comb. The colony survives not because flowers are always available, but because bees prepare for the possibility that resources may suddenly become limited. Agricultural societies stored grain after harvest seasons because winter or drought could reduce future food supplies. Families preserved fruits, vegetables, and meats before refrigeration existed because fresh food availability changed year-round. Reservoirs collect water during rainy periods to support cities during dry seasons. Across nature and human civilization alike, survival often depends upon storing resources during abundance in preparation for future uncertainty. The reserves provide concentrated energy that sustains thousands of bees when conditions outside no longer support reliable nectar gathering. During colder seasons, bees may remain clustered inside the hive while consuming stored honey slowly to support movement and warmth generation. During storms or prolonged poor weather, reserves allow the colony to survive even when foraging becomes temporarily impossible. A useful detail in honey production is how the honey reflects the environment where it was created. The flavor, aroma, color, and composition of honey all depend heavily upon the plants visited by the bees and the conditions affecting nectar production during that season. Rich wildflower blooms may produce complex, fragrant honey, while drought-stressed landscapes may yield smaller harvests with different characteristics. The hive itself becomes a living record of conditions unfolding outside across the landscape. Productive flowering seasons may leave the colony with large sections of capped honeycomb and strong reserves. Poor bloom years may limit storage and increase pressure on the colony later during scarcity. Weather patterns, climate, rainfall, soil conditions, plant diversity, and seasonal timing all shape the quantity and quality of honey preserved inside the hive. Bees respond to these environmental changes through instinctive behavior. During periods of abundant nectar flow, foraging activity intensifies while interior bees process incoming liquid continually. During scarcity, the colony may conserve energy and rely more upon existing stores. Thousands of bees cooperate together while adjusting to conditions far beyond the hive. The honeycomb resting inside the colony represents more than stored sweetness alone. Each sealed cell contains preserved energy gathered from flowers shaped by sunlight, rainfall, soil, climate, and season. The reserves reflect the health and productivity of the surrounding ecosystem, because bees depend entirely upon flowers for the nectar used to create honey in the first place. Among the most remarkable parts of the hive is the honeycomb itself, a structure so efficient and organized that scientists, engineers, architects, and mathematicians have studied it for generations. At first glance, the comb may appear simple. Rows of repeating wax cells spread outward across flat sheets inside the hive, while bees move continually across the surface. Yet hidden within this structure is one of nature's most effective examples of geometry, working in support of survival. Every part of the comb balances strength, storage capacity, stability, and material efficiency in ways that allow the colony to preserve large amounts of honey while using small amounts of wax. The repeating pattern found throughout the honeycomb is immediately recognizable. Each cell forms a hexagon, a shape with 6 sides fitting tightly against neighboring cells without leaving wasted gaps between them. Thousands of these repeating hexagonal chambers combine into large interconnected surfaces that can hold honey, pollen, and developing bees inside the hive. The arrangement appears orderly and architectural, yet it emerges entirely through the instinctive behavior of bees shaping wax together inside the colony. One reason the hexagonal pattern is so important is because it maximizes available storage space while minimizing the amount of wax required for construction. If bees built circular storage chambers, empty gaps would remain between neighboring cells. Square or triangular cells could fit together without gaps, yet those shapes would require more material to enclose the same amount of storage volume. The hexagonal arrangement solves both problems at once by allowing tight, efficient packing while also reducing the total amount of wax needed for the walls. Humans encounter similar ideas throughout engineering and construction. Bridges rely upon shape supports that balance strength and material efficiency. Modern packaging often uses repeating geometric forms to reduce wasted space during transport and storage. Floor tiles, bricks, and architectural frameworks frequently repeat patterns because repeating shapes provide organization and stability. Inside the hive, bees arrived at an effective solution before human mathematics formally described these geometric principles. The efficiency of the honeycomb becomes even more impressive when considering the cost of wax production itself. Bees must consume a large amount of honey to produce relatively small quantities of wax from specialized glands beneath their abdomens. Wax represents a valuable resource for the colony, and minimizing waste becomes important. By building hexagonal cells, bees create strong storage chambers while using less wax than many alternative arrangements would require. The structure of the comb must also support significant weight. Mature honey becomes heavy once thousands of cells fill with concentrated liquid. Entire sections of comb may hold much stored honey suspended vertically inside the hive, while bees continue moving across the surface. The repeating geometry distributes this weight throughout the structure, helping the comb remain stable despite constant activity and changing loads across different areas of the hive. Strength emerges naturally from the way neighboring cells support one another. Each wall becomes shared between adjacent chambers rather than existing independently. This interconnected arrangement allows the comb to function like a single unified structure where stress spreads across many cells rather than concentrating heavily in isolated sections. Engineers studying natural structures often admire honeycomb for precisely this reason, because the design combines lightness with impressive structural stability. Inside the hive, bees continue expanding and repairing the comb as needed, while maintaining its repeating geometry with remarkable consistency. Fresh wax appears soft and pale, before slowly hardening into durable comb structures that can last for extended periods inside the colony. Bees shape, smooth, and connect the wax while constructing rows of tightly fitted cells extending across the interior of the hive. A useful detail in honeycomb construction is that no single bee oversees the design as a human architect might direct a building project. Individual bees respond instinctively to structures, temperature, crowding, and the position of neighboring bees, while slowly extending the comb through many small actions. Yet despite the absence of centralized planning, the final structure emerges with remarkable regularity and efficiency across the hive. The geometry of the comb influences nearly every part of life inside the colony. Storage cells hold nectar and honey. Other sections support developing larvae and pupae. Bees move across the repeating surfaces while transporting food, ventilating the hive, cleaning cells, and maintaining the colony. The arrangement allows thousands of bees to navigate crowded interior spaces while preserving organization inside the hive. The repeating pattern also supports airflow and environmental regulation inside the colony. Open spaces between comb sections allow warm air and moisture to circulate, while bees continue ventilating the hive through wing movement. Every part of the structure contributes into honey production because stable storage, evaporation, movement, and organization all depend upon the arranged geometry of the comb. Humans often describe honeycomb as beautiful because the repeating hexagonal pattern feels orderly and balanced to the eye. Yet inside the hive, beauty is secondary to function. The structure exists because it solves multiple problems simultaneously. It maximizes storage. It conserves wax. It distributes weight. It supports movement. It organizes the colony. It protects reserves. Through geometry alone, the hive achieves remarkable efficiency without wasting precious energy or material. Outside the hive, flowers continue blooming across fields, orchards, forests, and gardens, while bees travel outward, gathering nectar from the landscape. Inside the colony, however, the honeycomb stands as the physical foundation supporting every stage of honey production and storage. Thousands of hexagonal cells hold reserves gathered through many flights, while the repeating structure maintains strength and organization inside the hive. Deep within the darkness of the colony, rows of repeating wax chambers stretch across the comb in connected patterns shaped entirely through instinct and cooperation. The geometry of the hive supports the survival of thousands of bees by creating one of nature's most efficient storage systems, where strength, organization, and preservation emerge naturally from the repeating structure of the honeycomb itself. The efficiency of the honeycomb becomes even more remarkable when examined from the perspective of energy and material use inside the colony. Every part of the hive depends upon careful balance, because producing wax, gathering nectar, ventilating the hive, and maintaining thousands of living bees all require significant energy. The colony cannot afford unnecessary waste. Honeybees rely upon structures and behaviors that maximize storage, while minimizing the amount of material and labor required to support survival. The design of the honeycomb reflects this principle throughout every section of the hive. Wax production alone demands a great deal of effort from bees. In order to create wax, bees consume stored honey and convert portions of that energy into tiny wax scales secreted from specialized glands beneath the abdomen. A relatively small amount of wax may require the consumption of large quantities of honey by the colony. Because wax is so energetically expensive to produce, the hive benefits from any structural design that reduces material use without sacrificing strength or storage capacity. The repeating hexagonal arrangement of the honeycomb achieves exactly that balance. Each cell shares walls with neighboring cells, meaning less wax is required overall, compared to structures where every chamber would need separate walls. The geometry allows bees to enclose large storage volumes using minimal building material. In practical terms, this means the colony can devote more energy toward gathering nectar, raising young, and maintaining reserves, rather than endlessly replacing wasted construction material. Lightweight aircraft frames use arranged supports to reduce material while preserving strength. Storage warehouses organize goods to maximize available space. Bridges distribute weight through repeating structural patterns rather than relying upon solid, massive blocks of material. Across both nature and human engineering, efficient design often emerges when structures achieve maximum function using the least possible energy and resources. Inside the hive, storage capacity is important because the colony must preserve enough honey to survive periods of scarcity. Every additional section of effective storage space increases the hive's ability to maintain larger reserves during productive seasons. The comb functions not simply as shelter or decoration, but as the physical system supporting the lasting survival strategy of the colony. The arrangement of the comb also supports movement and organization inside the hive. Thousands of bees navigate across the wax surfaces while carrying nectar, feeding developing young, cleaning cells, ventilating the interior, and managing reserves. The repeating structure creates predictable pathways and organized regions where different tasks occur simultaneously without complete disorder, despite the large population living inside the colony. A useful detail in hive organization is how naturally it emerges through collective behavior. No single bee creates a master blueprint for the hive. Bees respond instinctively to local conditions, neighboring structures, scent signals, temperature, crowding, and the needs of the colony. Yet from these many small interactions emerges an organized environment where storage, food processing, brood care, ventilation, and movement remain coordinated across the entire hive. Storage cells hold honey securely while remaining accessible to bees when food becomes necessary. Open comb surfaces support evaporation during earlier stages of nectar processing. The arrangement of comb sections allows airflow to move through the hive, while bees regulate moisture and temperature conditions inside the colony. Every part of the structure supports multiple overlapping functions together. If spaces become too narrow, movement through the hive becomes difficult. If spaces become too wide, additional wax construction may occur to reduce the gap. The colony preserves a consistent internal arrangement, supporting both efficient movement and stable environmental regulation. This spacing allows thousands of bees to navigate crowded interior spaces while continuing the constant activity required for survival. The hive itself operates like a living city, organized around energy management and resource preservation. Nectar enters from the outside environment through the work of bees. The liquid moves through processing stages inside the colony before becoming concentrated honey stored safely inside sealed comb cells. Wax structures support storage and movement, while airflow regulates moisture and temperature inside the hive. Every action inside the colony contributes in some way toward maintaining organization and preserving survival. Remarkably, this efficiency emerged through natural selection over immense time rather than through conscious invention. Colonies that used resources survived more successfully than colonies wasting energy or materials in. Across millions of years, behaviors and structures supporting stability, organization, and efficient storage became deeply refined within honeybee biology and colony behavior. Outside the hive, flowers continue changing with weather, sunlight, rainfall, and seasonal conditions. Inside the colony, however, the organized structure of the comb supports a controlled environment where preserved honey rests safely within optimized storage chambers. Thousands of bees move through this organized interior while maintaining one of nature's most efficient systems for food processing and lasting resource storage. Deep within the darkness of the hive, every wax wall, every repeating cell, and every organized passageway reflects the colony's constant balance between effort and survival. Material use remains minimized, while storage capacity grows as large as possible within the available space. Through geometry, cooperation, and instinctive organization, the hive achieves remarkable efficiency while supporting the preservation of the honey reserves upon which the colony depends. Although honey is often spoken about as if it were one single substance, the reality is more varied and closely connected to the environment where it was produced. Honey gathered from one region of the world may look, smell, and taste different from honey produced somewhere else, because the flowers visited by the bees shape nearly every characteristic of honey. The nectar collected from blossoms across forests, orchards, gardens, mountains, grasslands, and wildflower fields carries subtle chemical differences influenced by plant species, climate, soil conditions, rainfall, and season. As bees transform this nectar into honey, traces of the landscape remain preserved within the finished reserves stored inside the hive. Some honey appears pale gold and delicate, while other varieties become deep amber or nearly brown in color. Certain honey develops floral aromas, carrying hints of herbs, citrus, wildflowers, or forest plants, while other kinds may taste rich, earthy, or slightly smoky, depending on the environment where the nectar originated. They begin naturally inside the flowers themselves, because each plant species produces nectar with its own chemical composition. Flower nectar contains more than simple sugar dissolved in water. Tiny amounts of aromatic compounds, minerals, acids, and plant-produced chemicals also enter the liquid and later influence the characteristics of the honey created from it. A field of clover flowers may produce nectar quite different from the blossoms of lavender plants, eucalyptus trees, orange groves, mountain wildflowers, or forest shrubs. When bees gather nectar from one major flower source, the resulting honey often carries recognizable characteristics connected to that plant community. Grapes grown in different regions produce wines with distinct aromas and flavors influenced by soil, rainfall, sunlight, and climate. Coffee beans from separate mountain regions may taste dramatically different despite coming from the same general type of plant. Even fruits and vegetables grown in varying climates often develop noticeable differences in sweetness, texture, or aroma. Honey reflects this same intimate connection between environment and final flavor, because the landscape itself contributes to the nectar gathered by the bees. Location plays a major role in shaping the honey stored inside the hive. Colonies living near citrus orchards may produce honey carrying light, fragrant citrus notes, while bees gathering nectar from alpine wildflowers in mountain regions may create entirely different flavor profiles influenced by cooler climates and seasonal blooms. Forest environments, grasslands, coastal areas, deserts, and agricultural regions all provide different combinations of flowers that later shape the honey created inside the colony. Seasonal timing also influences variation inside the hive. Early spring blossoms may produce nectar different from flowers blooming during midsummer or autumn. In some regions, bees collect nectar from changing waves of flowers as the season progresses, meaning the composition of the stored honey may shift slowly year-round, depending on which plants dominate the landscape at different times. Bees gather nectar according to availability, abundance, distance, weather conditions, and communication inside the colony. Yet through these many foraging decisions, the hive unintentionally captures the character of the environment inside the honey. Every stored reserve becomes a kind of natural record, reflecting the plants and conditions present during the period of nectar collection. A useful detail in honey variation is that even neighboring regions may produce noticeably different results if local vegetation changes. A hive placed beside fields of flowering herbs may create honey, unlike another hive located near forests or fruit orchards only a short distance away. Soil chemistry, rainfall patterns, altitude, temperature, and local biodiversity all influence which plants thrive within a region, and those plants later shape the nectar available to bees. Inside the hive, however, the transformation process remains fundamentally the same, regardless of flavor or origin. Nectar arrives from the landscape through the work of thousands of bees. Enzymes begin altering the sugars, while moisture decreases through evaporation and airflow. Honeycomb stores the thickening liquid, while bees regulate conditions inside the colony. Yet despite these shared biological processes, the honey still carries distinct traces of the flowers and landscapes from which it began. Humans have valued these regional differences in honey for thousands of years. Certain varieties became prized from unusual aromas, colors, or textures linked to particular environments. Some honey remains light and mild, while others become bold and intense. Crystallization patterns may differ depending on sugar composition. Even the scent released when opening a jar can reveal subtle hints about the flowers visited by the bees during nectar gathering. The connection between honey and place reveals how deeply the hive remains tied to the ecosystem surrounding it. Bees cannot create honey independently from the environment, because every drop begins with flowers shaped by climate, weather, soil, sunlight, and season. The colony depends entirely upon the landscape beyond the hive entrance. Forests, orchards, grasslands, gardens, mountain meadows, and agricultural fields all become part of the honey preserved inside the comb. One of the most noticeable things about honey is the large variation found in its appearance from one region or flower source to another. Some honey pours with a pale golden glow, transparent beneath sunlight, while other varieties appear deep amber, reddish-brown, or nearly dark enough to resemble polished wood. The texture may also vary. Certain honey remains thin and flowing for long periods, while other kinds become thick, creamy, or heavily crystallized depending on their composition and environmental origin. These differences are not signs that something has gone wrong inside the hive. The color of honey is influenced heavily by the plants from which the nectar originated. Different flowers produce nectar containing different combinations of sugars, minerals, aromatic compounds, acids, and trace plant chemicals. As bees gather and transform this nectar into honey, many of these subtle characteristics remain present within honey. Light-colored honey often comes from certain blossoms including clover or orange flowers, while darker varieties may develop from forest plants, buckwheat flowers, or particular tree blossoms, rich in more complex compounds. Composition and color are often connected closely together. Darker honey may contain different mineral levels or aromatic compounds compared to lighter varieties, while some pale honey develops delicate floral scents and mild sweetness. None of these variations make one honey universally better than another, because every type reflects the conditions and plant communities surrounding the hive where it was produced. Apples vary enormously in sweetness, texture, and color, depending on the variety and growing conditions. Tea leaves grown in separate mountain regions develop distinct aromas influenced by climate and soil. Even water flowing through different geological regions may carry unique mineral characteristics. Honey follows this same principle because it forms from nectar gathered across living landscapes shaped by weather, vegetation, and season. The diversity found in honey also reveals how connected bees remain to the ecosystem surrounding the hive. A colony located near citrus orchards may create light, fragrant honey with subtle fruit-like aromas, while bees foraging among mountain wildflowers may produce honey carrying entirely different scents and colors influenced by alpine plants. Forest regions often create darker, more earthy honey compared to open grasslands filled with clover or flowering herbs. Every environment leaves its mark upon the nectar gathered by the colony. Rainfall, temperature, drought, sunlight, and bloom timing all influence the nectar available to bees during any given year. Even hives located in the same region may produce slightly different honey from one season to the next, depending on which flowers dominated the landscape during peak nectar flow periods. Nature itself remains continually changing, and the honey produced by the colony reflects those shifts. Inside the hive, however, the bees process all incoming nectar through the same fundamental biological system. Bees gather nectar from flowers and transport it within the honey stomach before transferring it to other bees deeper inside the colony. Enzymes alter the sugars, while evaporation reduces moisture content, through airflow and ventilation. Honeycomb stores the liquid as it thickens slowly towards stable, preserved honey. Crystallization patterns also vary naturally between different honey, because sugar composition influences how quickly crystals form within the stored liquid. Some honey remains smooth and fluid for long periods, while others become cloudy, creamy, or grainy over time. These changes often surprise people unfamiliar with raw honey, yet crystallization is usually a natural physical process rather than spoilage. Temperature and sugar balance strongly influence how rapidly crystals develop inside stored honey. The scent released from honey can also reveal hidden details about its origin. Floral honey gathered from spring blossoms may smell light and fragrant, while darker varieties from forests or late-season flowers sometimes develop deeper, richer aromas. Bees unintentionally preserve traces of entire landscapes within the honey through the nectar gathered from thousands of blossoms across the environment. Variation inside natural products is very common throughout nature because nature does not produce identical outcomes in every place or season. Soil chemistry differs from region to region. Weather changes continually. Plant communities shift with climate and geography. Water availability rises and falls across landscapes. Bees respond to these conditions while collecting nectar, meaning the honey stored inside the hive naturally reflects this diversity. Humans often try to standardize products through industrial processing, so every bottle or package appears identical. Yet raw honey reminds people that natural systems rarely behave with perfect uniformity. The differences in color, aroma, texture, and flavor all reveal the biological complexity hidden behind what may seem at first like a simple food. Each jar preserves traces of flowers, weather, season, geography, and the collective activity of thousands of bees moving across the landscape. By the time honey rests preserved in the honeycomb, the process reveals something much larger than the activity of bees alone. Honey production connects insects, flowers, climate, soil, weather, water, sunlight, and entire ecosystems together through one continuous chain of interaction unfolding across nature. Every drop of honey begins far outside the hive, among living landscapes filled with plants competing for light, moisture, and pollinators. The colony depends upon these surrounding environments, because without flowers, there would be no nectar to gather and no honey to preserve. Bees rely heavily upon flowers, not only for nectar, but also for pollen, which provides important proteins and nutrients supporting the colony. Flowering plants act as the foundation beneath nearly every stage of honey production and hive survival. Forests, orchards, gardens, grasslands, mountain meadows, wetlands, and agricultural fields all become part of the system supporting bee activity, because each environment contributes different flowering species across changing seasons. At the same time, flowers also benefit enormously from the movement of bees between blossoms. As bees travel outward gathering nectar, pollen grains attach to the tiny hairs covering their bodies and later transfer to other flowers during future visits. This pollination process supports plant reproduction across entire landscapes. Seeds develop, fruits grow, plant populations continue spreading through forests, fields, and orchards because pollinators move pollen between blossoms while searching for food. Many flowers evolved alongside pollinating insects over immense time. Bright petals, floral scent compounds, ultraviolet markings invisible to human eyes, and nectar production itself all help attract pollinators, including bees. Some flowers even develop shapes that guide insects toward hidden nectar chambers, while positioning pollen along the bee's body during each visit. Bees receive food, while plants receive reproductive assistance through pollination. Yet many plants across the world rely heavily upon insects to reproduce successfully. Orchards producing fruits, fields filled with flowering crops, wild plants supporting animal habitats, and forests containing diverse flowering species all benefit from pollinators moving across the landscape. The simple act of a bee visiting flowers supports much larger ecological systems extending far beyond the hive. A useful detail in honey production is that the hive gathers energy from the wider environment and concentrates it inside the comb. Sunlight powers plant growth through photosynthesis. Flowering plants produce nectar using energy captured from the sun. Bees gather that nectar and transform it into honey through biological processing and evaporation inside the hive. The reserves stored under wax contain concentrated energy that originally entered the ecosystem through sunlight reaching leaves and flowers across the landscape. The health of bee colonies often reflects the condition of the environment, because bees depend so heavily upon flowering diversity and stable ecosystems. Landscapes rich with varied flowers generally provide stronger nectar resources across longer portions of the season, while damaged or simplified environments may reduce food availability for pollinators. Weather patterns, drought, habitat loss, pesticides, disease, and environmental disruption can all influence the complex relationships connecting bees, flowers, and ecosystems together. Inside the hive, however, the colony continues responding to these changing conditions through collective behavior and constant activity. Bees adjust foraging patterns according to nectar availability, while the colony manages reserves during periods of scarcity. Every stage of honey production remains connected to conditions unfolding outside among the flowers and landscapes supporting the bees in the first place. Natural systems rarely function in complete isolation. Forests influence rainfall and soil stability. Flowering plants support pollinators. Pollinators support plant reproduction. Plants provide food and habitat for many other organisms across the ecosystem. Even the honey stored inside the hive represents the final result of interactions extending through many layers of nature. Climate shapes flowering seasons. Soil influences plant growth. Water availability affects nectar production. Bees respond to all of these conditions simultaneously while gathering resources from the environment. Agriculture across much of the world benefits heavily from pollination provided by insects including bees. Many fruits, nuts, vegetables, and flowering crops depend partly or heavily upon pollinators for successful production. Gardens bloom more successfully because insects move pollen between flowers. Entire food systems remain linked to these quiet ecological interactions happening across fields and landscapes around the world. Remarkably, honey production reveals these large ecological connections through something small and familiar enough to fit inside a spoon. A jar of honey may appear simple resting on a kitchen shelf, yet hidden inside it are traces of sunlight, flowers, climate, rainfall, soil, pollination, evaporation, chemistry, geometry, and the labor of thousands of insects working together across the landscape. From the outside, a beehive may appear quiet and ordinary, resting beneath trees, beside gardens, or along the edges of flowering fields. Yet hidden inside that enclosed space is a remarkable system found anywhere in nature. Thousands of bees cooperate through instinct, communication, chemistry, airflow, geometry, and collective behavior to transform fragile nectar into preserved honey that can sustain inside the colony through changing seasons and environmental uncertainty. Every stage of the process depends upon many small actions unfolding together inside the hive, while the landscape provides the flowers and nectar supporting the system. The journey begins far from the honeycomb itself, among blossoms opening beneath sunlight across forests, orchards, meadows, grasslands, farms, and gardens. Flowers produce nectar to attract pollinators, while bees travel outward, searching for these hidden food sources across the landscape. Tiny droplets of sweet liquid gathered flower by flower become the raw material supporting the colony. The scale of the work involved is difficult to imagine because each individual bee contributes only very small amounts during each foraging trip, yet thousands of repeated flights slowly build the reserves later stored inside the hive. Once nectar returns to the colony, biology and chemistry immediately begin working together inside the hive. Bees transfer nectar between one another, while enzymes start changing the sugars hidden within the liquid. The hive then supports evaporation through airflow, warmth, and organized storage inside wax comb. Moisture slowly leaves the nectar, while sugars become increasingly concentrated over time. The transformation unfolds through patience and environmental control, rather than sudden dramatic change. One of the most remarkable aspects of honey production is how many separate systems operate together simultaneously inside the colony. Bees gather nectar outside, while interior bees process incoming liquid across the comb. Other bees ventilate the hive through rapid wing movement, while wax-producing bees construct and maintain the honeycomb itself. Temperature regulation, airflow, storage organization, brood care, communication, and food preservation all occur together inside the hive together. The colony behaves like a single living organism composed of thousands of smaller individuals carrying out specialized tasks in support of collective survival. The honeycomb stands at the center of this organization. Repeating hexagonal cells provide efficient storage while minimizing wax use and supporting remarkable structural strength. Open cells allow evaporation during early processing stages, while sealed cells later protect honey from excess moisture and contamination. Every section of comb supports movement, airflow, storage, and organization inside the hive. Through geometry alone, the colony creates one of nature's most efficient systems for preserving reserves. Honey itself reflects the environment from which it originated. Different flowers produce different nectar compositions, meaning the color, aroma, texture, and flavor of honey vary depending on the landscape visited by the bees. Forest blossoms, wildflowers, citrus orchards, mountain meadows, grasslands, herbs, and flowering trees all leave subtle traces within the honey stored inside the comb. The preservation of honey may be a remarkable outcome of the process. Fresh nectar begins as thin, watery liquid vulnerable to spoilage, yet through evaporation and sugar concentration, the colony slowly transforms it into a stable, lasting food reserve. Low moisture levels, concentrated sugars, enzyme activity, and careful storage combine to create conditions unfavorable for microbial growth. What began as fragile nectar ultimately becomes preserved nourishment, able to last through long periods of scarcity. For the bees themselves, honey is not created as a luxury or decoration. The colony depends upon these reserves for survival during colder months and difficult conditions when flowers disappear from the landscape. Every sealed cell represents preparation for the future. Bees gather nectar during abundance, so the colony can endure scarcity later through preserved energy stored safely inside the hive. The process also reveals how deeply connected natural systems truly are. Flowering plants rely upon pollinators for reproduction, while bees rely upon flowers for nectar and pollen. Climate shapes flowering seasons while soil and rainfall influence plant growth. Ecosystems support the landscapes where bees forage, and pollination later supports forests, orchards, gardens, and agricultural systems across the world. Honey production connects insects, plants, weather, chemistry, geometry, and ecology together through one continuous chain of relationships unfolding across nature. For thousands of years, humans have been fascinated by honey because it combines simplicity and complexity in such an unusual way. A spoonful of honey seems calm and familiar, yet hidden inside it are traces of millions of flowers, many bee flights, environmental change, biological chemistry, and remarkable collective labor carried out inside the hive. Ancient people valued honey before modern science existed because they recognized something special within this preserved golden substance gathered from nature. Even today, the quiet activity of bees continues everywhere flowers grow. Across forests, gardens, mountain valleys, orchards and grasslands, bees still travel between blossoms, gathering nectar beneath shifting sunlight and changing weather. Inside the hive, the transformation continues, just as it has for millions of years. Nectar moves through the colony. Air circulates through the comb. Moisture leaves the liquid. Wax cells fill with reserves while the hive prepares for survival. Deep in the honeycomb, biology, chemistry, geometry, airflow, and cooperation all come together through the work of thousands of bees moving through the colony. What began as delicate nectar hidden inside flowers becomes concentrated honey stored safely under wax inside one of nature's most organized living systems. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about how honey is made. Good night.